This is part 6 of the Module 7 lecture. In this case, we're going to see how to construct a confidence interval, what are its characteristics, and how it's interpreted. All right, let's, as an example, let's construct a 95% confidence interval for the population mean mu. Now we're going to assume that the sampling distribution of the mean is normal and that the population standard deviation sigma is known. Now you recall from the definition of the standard the definition of the sampling distribution of the mean, that its mean is just the mean of the population and its standard deviation is just the standard deviation of the population divided by the square root of the sample size. All right. Now we want this 95% confidence interval, which is defined by these two averages, where we believe the population mean lies with a 95% level of certainty. So in other words, we're saying that we want these two limits to bound the mean and have a 95% probability that the mean is within these two numbers. Now, because this is a symmetric interval around the mean, so since we have 95% here, we have 5% outside. And because this is symmetric, we split the remaining probability 0.05 between the two, what we call the two tails. So you see that the probability on the left side, on the left tail, is alpha over 2 or 0.025. And on the right is the same, alpha over 2 or 0.025. So we would like to find these two values, x, the low average and the high average, that are the bounds of this confidence interval. And in 95% confidence interval to be precise, because we now know all these probabilities. All right, so how do we find this? Well, we're going to use what we learned in chapter 6. So from these probabilities, we're going to find the z-values on table 4. And so if you look at your table 4, you will see that for a probability of 0.025, the z-value is minus 1.96. And because the area on the upper tail is the same as on the left tail, or the lower tail, then we know by symmetry that the z-value on the right-hand side is 1.96, but positive. So now if you remember in chapter 6, once we found the z-value, we can find the x-value using an equation like this. So we want to find this x, this average low. And if you remember, that equation was the population mean minus minus the z-value times the standard deviation of the, in this case, of the sampling distribution, which is sigma divided by the square root of n. But you say, wait a second, you said mu, oh, by the way, and this is the same equation, except that here we're using the positive z-value. But in both cases, I'm not using the population mean as we did in chapter 6. Well, you say, why are you doing that? Well, because we don't know what the value of mu is. This mean of the population is unknown. But we learned that the best estimate of mu, well, is a point estimate. Well, that's the only estimate we have. So instead of using mu, we use the point estimate as our best guess as to what mu is. And so we construct this, we find these limits of the confidence interval based on the point estimate of the population mean. So these two are the limits of the confidence interval. So, and here it's very important to realize that the confidence interval limits, this x low and this x high, as well as the sample statistics that we use to calculate it from, this the point estimate specifically, they're all random variables that change with every new sample due to sampling error. So if you take a sample and construct a confidence interval, and then you take another sample and construct another confidence interval in identical manner, they may not be exactly the same because the point estimate is different for each sample. And also note that the population parameter, mu, is a fixed number. That's a fixed value. that may or may not be in the confidence interval because it is built around the point estimate. And remember, the point estimate moves. And if you remember in that simulation we did with a six-sided die, we have some averages that were a little way too far, whereas others were close. So those, when the average is too far from the mean, very likely that confidence interval may not contain the parameter. And this is what I'm illustrating with this figure. So we have this is the population distribution. Here's the population mean. And here we took multiple samples. And each confidence interval is for each of these samples. And you see this, the middle bar is a point estimate. And this is the width of the confidence interval. These are the limits, the low and the high limit. And you see the point estimate is moving around. But in most of the cases, the population mean is within the confidence interval, except in this one. So here, the point estimate just lies a little too far from the population mean that the confidence interval does not contain the population mean. And we know that in repeated sampling, in the long term, we're going to find that 95% of these 95% confidence intervals do contain the population mean, and 5% do not contain it. So this is important because then you say, well, if I calculate a confidence interval, how do I interpret that confidence interval? Well, you may say the theoretical interpretation, or what we call the correct interpretation, and the one that uses your textbook, that your textbook uses, it says if a large number of samples of the same size are collected and a confidence interval is constructed for each sample, approximately 95% of these intervals will contain the population mean. Well, that's great, but in practice, we only have one sample. So that confidence interval based on that single sample, well, it may or may not contain the population mean. And we do not know that. So if you happen to have gotten a point estimate that's too far, and we don't know if it is too far because we don't know mu, and that confidence interval does not contain the population mean, well, you are very unlucky because there is only 5 out of, or 5% of those will not contain the mean, but 95% of them will contain. So how do we interpret a single confidence interval? Well, we take it as if it does contain the mean. So we say the population mean is believed to be within the interval from x low to x high with a 95% confidence level. So we don't use the word 95% certainty. We do not say 95% probability because we do not know. We don't know. And the confidence interval either contains a mean or does not contain the mean with 100% probability. So we cannot say that there is a 95% probability that this single confidence interval contains the mean. We cannot say that. So this is a way to interpret the confidence interval. We simply say that we believe that the population mean is within these two values, these two limits, and we calculated that at a 95% confidence level. That's all we can say. But in practice, we assume that that single confidence interval does contain the mean. So keep that in mind, because this is the language that we will use to interpret the confidence interval. This one for a single confidence interval. All right. Now, the characteristics of the confidence interval is its width. Very important. So the width of the confidence interval is going to decrease if you increase the sample size. Why? Because the standard error decreases as the sample size increases. And you can see it here in the expression of the confidence interval. So as n increases, this quantity gets smaller and this confidence interval gets narrower. But on the other hand, if you want to increase the level of confidence, then the width of the confidence interval is going to increase. Why? Because if 1 minus alpha is larger, the closer it gets to 1, the smaller these probabilities are going to be. So these probabilities are going to move away as you increase the level of certainty. And that as they move away, the z-value gets larger and larger. And you can see from the confidence interval, if this value gets larger and larger, well, the width of the confidence interval is going to increase. And I think I assigned a homework problem where I ask you to calculate the confidence interval for different levels of confidence, and you see how it does increase. All right, I'm going to stop here. In the next section, we're going to start now using that definition of the confidence interval and start calculating confidence interval limits.